So now let us calculate these two probabilities. So this one is first is probability that b x prime minus x is 0, right, given bx is minus b. That's the same event, because once bx is minus b, you can replace minus b by bx and then subtract and get this equality to 0. And probability that bx is minus b, this we have calculated before, right? This we have calculated as 2 raised to minus k. Now in this first probability, this bx minus b is not playing any role anymore, right? Because x prime is a different variable. So we can as well write this to be probability of the event that x prime bx prime minus x is 0. That's the same probability, which again is 2 raised to minus k. So you get 2 raised to minus 2k, okay, as claimed. That's the idea. That's the, in fact, the detailed proof. And moving on to the third property, which is the most relevant to our application. This will come from the top two. Okay, so let consider the random variable n. We will define n to be the number of x's in S which under the random hash function vanish, go to the 0 bucket. Okay, so this is a random variable because we are counting this count will actually depend on the random choice of the hash function. Okay, so as age changes, this number n may also change or will change. So what we are interested in is, when is this number 0, when is it 1, and when is it more than 1, right? Those are the events out of which we are interested in. When is it 1? What's the probability? So let's calculate that. So by inclusion exclusion principle, we can write that probability. So we will calculate n greater than or equal to 1, greater than or equal to 2, then we can take the difference. Okay, so that's what we will do. We calculate the probability that n is greater than or equal to 1 and n is greater than or equal to 2. Okay, these two probabilities we will calculate, and then the difference will give us when is it 1. What is the probability that n is 1? So let's implement that idea. So probability that n is at least 1, this is by inclusion exclusion principle. Go over all the x's in S. Probability that for random age hash function x vanishes. But when we do this sum, we are over counting where in the cases when each is mapping x and x prime both of them to 0, right? So then that event we are counting in hx equal to 0, but also in hx prime equal to 0. So, we will subtract that to remove the double counting. So, x less than x prime in S, probability that hx is hx prime is 0. Okay, but now when we subtract, we are undercounting because we have we have subtracted this x prime and x prime prime, right? That we have subtracted too many times. So, anyways, we only wanted a lower bound, so the lower bound is correct by inclusion exclusion principle. So, probability of n greater than or equal to 1 is at least this much, this thing that we have undercounted, and so now we can simplify it. So, first is properties shown in the claim, right? We get that this is 2 raised to minus k, and the next one is size of S choose 2 many xx primes, and both x and x prime going in the same bucket, that probability is 2 raised to minus 2k. Okay, so we have done half the part. Probability of n greater than or equal to 1, we have a lower bound. Next is to estimate n greater than or equal to 2. So, similarly, probability of n greater than or equal to 2, here we will need an upper bound, because remember we will subtract these two, right. So, and we need a lower bound on n equal to 1. So, it suffices to have an upper bound on n greater than or equal to 2. So, here just go over all the pairs x prime, right, because you want at least 2 to go in this bucket. So, this is simply smaller than this event, x less than x prime in S, which we have calculated as before. So, this is just equal to S choose 2 raised to minus 2k, and so what you get is probability n equal to 1 for random hash functions given by changing big B and small b. So, that probability is probability n greater than or equal to 1 minus probability n greater than or equal to 2, which is at least, so lower bound S 2 raised to minus k minus S choose 2 raised to minus 2k, and then you subtract again the same thing. So, 2 times this, right, and you can check that this is at least S by 2 raised to k minus S by 2 raised to k whole square. Okay, the first is S by 2 raised to k, the second is just square of that being subtracted. You can check that this inequality is satisfied, it's almost the same. And what can we say about this now? So, here we will use the hypothesis. What was the hypothesis? The hypothesis said that S is between 2 raised to k minus 2 and 2 raised to k minus 1. right? So that tells you something about s by 2 raised to k. It's between 1/4 and half. So use that. It's more than half, 1/4, and so using estimate, you can actually show that this is 1/4 minus 1/4 square, okay, which is greater than 1/8. So here you use the following property, basically show that this x minus x square function is increasing when x is less than half. Okay, so below x it is an increasing function. So using that we get the lower bound. We fix at 1/4 and get the value. That's the lower bound because s by 2 raised to k is between 1/4 and 1/2. Yeah, so that finishes this part of the proof. And so where are we? We have done the claim completely. Properties claim, the hashing claim is done. Properties 1, 2, 3. Now let us go back to the lemma, Valiant-Vazirani. Let's continue with. So lemma proof continues here. So what is the lemma demanding? That if phi has satisfying assignments, then essentially show that the satisfying assignments will be reduced to exactly one satisfying assignment and hence odd. So let phi have n variables. So randomly pick k between 2 to n plus 1. Why 2 to n plus 1? Well, because we need property 3, in property 3 we need s to be at least 2 raised to k minus 2, and we know that in the case of phi s is at least 1. So we can start with k equal to 2 and go up to n plus 1, because we don't know how many satisfying assignments there are, right? So just guess it or pick it randomly. So randomly pick k and b and small b. Okay, so whatever we don't know, we are just randomly picking, which is what is k, what is big B, what is small b. That fixes the hash function. And once we have this random hash function, we can look at the bucket 0. So what you do is output the Boolean formula psi, which continues to have n variables, as phi, and this extra condition that x maps to 0 bucket. So this, in case you are wondering, this condition can be written as a Boolean formula. So write it as a Boolean formula. It's not that difficult because you can think of a linear combination of x1 to xn using 0, 1 coefficients, setting it equal to 0, right. So, say x1 plus x2 equal to 0. So, that you can actually write as using and or not, because the constants are just 0, 1 and the addition is mod 2. So, mod 2 you can write in terms of and or not. So, do that, and then you have the formula psi, which is the Boolean formula out which this algorithm A outputs. Okay, this is a description of A. That is how A functions. So, immediately it is clear that if phi is unsatisfiable, then this AND condition cannot give you a satisfying assignment, right. It remains unsatisfiable. So, psi is also unsatisfiable. Right. So, s equal to 0 is going to s equal to 0. So, that is good. And second property is, if phi is satisfiable, then let S be the satisfying assignments. And its size is at least 1, that it is not an empty set, there is at least one element. And in fact, we can write the whole range. So, the whole range is 2 raised to 0 less than equal to 2 raised to n. This is the range for size of S, right. And this is the set on which the hash function does magic and makes the 0 bucket singleton. So, let us check the probability. So, with probability at least 1 by n, we would have chosen k. We would have chosen the unique k such that S is between 2 raised to k minus 2 and 2 raised to k minus 1. Right, there is only one k, and that k randomly, if you keep trying, then you will find with probability 1 by n, because k takes only around n minus 1 values. So, you will hit the correct one. So, conditioned on this fact or this choice, so conditioned on this event, with probability greater than 1 by 8, we choose big B and small b such that number of x's mapping to the going to the bucket 0 is 1. Right, this we have shown in Valiant Vazirani. This is exactly in this claim number 3, this is exactly what we showed, right, that with probability 1 by 8 this will be 1. So, which means that you multiply the probabilities. So, at least with probability 1 by A10, we would have K, P and B. So, hash function, we have chosen a hash function with this much probability such that number of satisfying assignments of psi is 1. Okay. Hence odd. Right. So, if phi, if hash phi is 0, then hash psi is 0, which is even. Otherwise, hash psi is 1, which is odd. And that proves both the parts of Valiant-Vazirani. So, this implies Valiant-Vazirani lemma. Right. So, that's a great result. In fact, it is showing not reduction to Parity-SAT, but unique SAT. So, we actually gave a randomized reduction of SAT. So, it's a polytime randomized reduction of SAT to unique SAT. Right, this is what we just showed, that you can actually assume number of satisfying assignments to be either is 1 or 0, only 2 options. If you can solve this problem algorithmically, then you can solve SAT also in practice. And we also showed NP to parity P. Right, these are the multiple interpretations of Valiant-Vazirani lemma. But what was our original goal? So, our original goal was this theorem of Toda, right? Polynomial hierarchy. So, we in particular sigma 2 NP to the NP. What about that? Can we reduce NP to the NP to Parity-SAT, which then reduces to sharp SAT? So, that we do not have any idea from this proof, right. So, we have to work hard on that. So, now we will use this idea repeatedly to random reduce pH to parity P. So, we intend to replace there exist for all quantifiers by a new quantifier parity. So, instead of using 2 quantifiers, because they start alternating and then we do not understand reduction to sharp SAT, instead of that we will convert them to single quantifier, which is this upcoming new quantifier, parity quantifier. So it has this interpretation, this natural interpretation that the variable, if it is acting on x, so parity x, what does parity x quantifier mean? It is true when the number of satisfying x's is odd. Okay, so we have in a way shown that there exist can be replaced by parity, and we will also show that for all can be replaced by parity. So let us define it, because this will be now our main notation. So for Boolean formula phi x, parity x comma phi x, this expression, so we are not saying for all x phi x or there exist x phi x, we are saying parity x phi x. This is true if the number of x's that satisfy phi is odd. Okay, that's the definition. Number of these x's on which parity is acting, if this is odd, then this quantification is true. And now even alternating there exists for all, we will convert all of them to this single one. So let's write that down, the result we intend to prove. So let's just call this lemma parity. Let C be a constant. There exists polytime Turing machine M or polytime Turing machine A such that for every quantified formula, for every formula phi or psi with C alternations, okay, C alternations of there exist for all, we have the following two properties. So first is if psi is true, then probability of this randomized reduction, right? So it uses random bits R and the input instance psi. This is Parity-SAT with a decent probability, with a very good probability, in fact 2/3 probability. And in the other case, when psi is false, then the probability of this is much smaller, less than 1/3. So note that if this is this may make a mistake both sides, right? In true also there are some mistakes, false also there are mistakes. So both sided errors are possible. So the error is happening, more error is happening than Valiant-Mazirani because of when you convert for all. Okay, then both sides there are errors. So we'll finish this proof next time.